I'm going to look at two different scenarios. One you may think of as a fairly low demand scenario when you're just, say, sleeping or resting or sitting here. The other is a high demand scenario when you think of, say, an athlete exercising. Typically, the low demand scenario would be the one that's most relevant in a medical context. You're probably not going to be having high-performing athletes coming in and needing these various medical treatments. But just to get a sense of what the range is, it's good to have both of these scenarios in mind. So first, let's have a look at oxygen transport to these robots. And here again is a cross-section through the tissue and the blood vessel. Here we're looking at a scenario with no robots, just the vessel by itself. And you see the streamlines of the fluid flow, nice and smooth, completely laminar at this tiny scale. And first we'll have a look at the low demand scenario. Again, the case with concentration with no robots. In this case, the red shows the concentration is pretty uniformly high in the blood and the tissue. The tissue is not using very much of the available oxygen. In this case in particular, the blood just has the oxygen. Only a small amount of it is actually used by the tissue and just returns to the lungs. We put a group of robots in there, and we see they draw down the concentration quite significantly. And it's particularly the blue goes down to 0. And I want you to notice here is the very high concentration gradients. And this is why kinetics is an important point to keep in this model. Let me show you the similar behavior in a high demand scenario. So this has been very, say, active muscle tissue. This is now without any robots, and you see now the tissue is drawing down quite a bit of the oxygen that the blood is delivering. But again, not a lot of it. If you look at the right, there's a lot of oxygen that's just flowing out from this segment of tissue. The tissue is unable to make use of, again, because of diffusion limits. You put the same robots in here, and again, you ask, these robots are just using as much oxygen as diffuses to them and competing with tissue for that. And you see, again, they draw down the oxygen quite a bit. And so we can ask two questions about this. One is how much power the robots get, and two, I'll come back to, is what are the consequences for the surrounding tissue. So first, power for the robots. What we see from this numerical study is that these groups of robots can get about some tens of picowatts. And this is just basically using all the oxygen that diffuses to their surface. And for comparison, the prototypical or nominal typical body cells use from 10 to 1,000 picowatts in their activity. And cells are quite a bit larger than these robots. And just another baseline for comparison, of you just sitting here, you're basically using 100 watts is a typical resting power use for a person. So the question is, okay, if we have some tens of picowatts, what could a picowatt be good for one of these robots? And what would these robots be doing? The kinds of things, if they're sitting around, they can be computing some interesting things, measuring some chemical concentrations and so on. A picowatt, even with sort of current laboratory demonstrated nanoscale electronics, so this is not particularly efficient, a picowatt could probably support something like 10 to the 5 logic operations per second. And by today's standards of computation and so on, that's not a lot. But if you compare it to, say, what a nanoparticle or drug delivery has, which is basically no computation whatsoever, 10 to the 5 operations per second can actually do you some reasonable amount of work on looking for interesting pattern recognition, some trends in concentrations, and so on. This amount of power could also be useful for communication among these robots. And although it's not part of this particular model where they're just sitting on the vessel wall, that kind of a scale of power could also enable these devices to move at about a millimeter a second through water or blood plasma by overcoming viscous drag. And that's typical or maybe a little bit faster than the rate that blood will generally flows through capillaries. So that's the results for what's the power from oxygen and glucose available to these robots? Now let me turn to the second question, which is, how might this affect the nearby tissue? If you're drawing down too much oxygen, will that mean that the tissue is in big trouble? So some possible questions are, you might worry about, well, if the robots are using oxygen, there's less available for the tissue. There could be issues of local heating because of the high power, the high power densities. You might worry about some waste products. That is, if you're consuming oxygen, you're producing more carbon dioxide than normally would be the case. And also the issues of forces on the vessel wall, because the robots are sitting there and dealing with fluid drag. I'm just going to look today at the first two of these issues. And so the first one is the robots are competing with the tissue for the same oxygen, and they also, for the section of vessel that they sit on, they're blocking the diffusion of oxygen out of the vessel, and so that could be a concern even if the robots were not using any oxygen at all, if they're just blocking the vessel. So let me go to the most extreme case that I showed you. This was the high demand scenario, and you're having the robots. Again, this is a cross-section through the tissue and the vessel. And let's have a look at the tissue power right next to the vessel and compare it to when the robots are there or not there. And here is a comparison based both for the low and high demand scenarios. And this compares to what the tissue would produce if oxygen were not limited at all. So basically an infinite availability of oxygen. That's the value of 1 at the top there. And you see that there's a drawdown, especially in the high demand scenario. But if you look at the numbers, actually it's not as dramatic a drawdown in terms of power as it is in terms of oxygen. And this is just because of the way that tissues generate power from oxygen. It's not at all a linear response. Second question is heating. You say, well, gee, these robots have a very high power density compared to cells of several orders of magnitude. Couldn't that cook the surrounding tissue? And so you can use the same model to quantitatively look at what happens with temperature, and indeed the temperature is higher by the robots, but if you actually look at the numbers, it's only a 10 to the minus 4 increase in the temperature. And that's because at these very small sizes, heat is also a diffusive process, diffuses away extremely quickly. And so for hundreds of robots, heating is not likely to be an issue. So let me summarize what I've told you from this model. You can expect tens of picowatts for micron-sized robots operating in capillaries. The oxygen is going to be taken additionally mainly from the passing red cells, relatively small reductions in tissue power, and insignificant local heating. I'd like to wrap up with just some additional biology questions. If any of you have some insights into these, I'd be more than happy to hear your suggestions and comments. There could be some other local effects. What about white blood cells when they go by? There are other functions of the blood than just delivering oxygen, such as immune response and so on. What effect might these robots have on that? And how might the cells on the vessel wall respond to the fact that the robots are sitting there? Are there some longer range effects? So I've talked about lower cell oxygen concentration when the robots take it out. So what happens downstream of where the robots are if the cells don't have as much oxygen? And so for some further information on this model and nanomedicine in general, here are a couple of websites. I particularly recommend the nanomedicine.com that Rob Freitas has put together. Thank you for your attention.